Hey everybody, greetings from my garage. I'd like to thank the organizers for inviting me to give a plenary at the IFAC World Congress, and I'd like to thank everybody for going above and beyond to make this Congress successful, even though we're subject to some really harsh constraints imposed by this global coronavirus pandemic. Obviously, it's a total bummer not to be in Berlin. For those who don't know, Berlin is my favorite city in the world. I lived there for a year. I love to travel and visit. And I'm optimistic that I'll be back there sooner rather than later. And until then, greetings from Berkeley. I'd also like to thank the organizers of IFAC for offering reduced registration fees to participate in this virtual Congress. I still feel like these talks should all be streamed for free, but I know that there are a lot of compromises and costs and constraints, so that wasn't entirely possible, and I really appreciate the organizers doing everything they could to make it as affordable as possible. So now, as a big disclaimer, this is the first time I've ever recorded a talk. I always just do it live. I feel like this is trying to record a stand-up show in front of an empty audience. It's really weird. It felt a little odd, but I feel like maybe I'll be able to adapt and get into this format at some point. But be warned, the production values are nothing to write home about. I gave it my best effort, and we'll see. Maybe the next one will be a little bit better. And I'm just kind of considering this like an experiment in podcasting, because the world really needs a control theory podcast. Maybe there is one. If there is one, I'm happy to participate. Send me an email. I'd love to jump on your control theory podcast. So without further ado, let me actually get to the meat of this talk, where we start to think about the intersection of machine learning and control in 2020 and where it's going. 2020 is an amazing time to give a keynote talk about autonomy, learning, and the future where these two fields might go together. I got a plot here of some amazing demos that have come out over the past couple years. Boston's dynamic robots doing impossible tricks, OpenAI trying to solve dexterous manipulation using very complicated machine learning tools, and Waymo partnering with Volvo and claiming that they're going to be sending us a whole army of robotaxis anytime soon. Now, of course, anybody who's been keeping track knows that 2020 was the year we were supposed to get auto taxis. Elon Musk said 2017, more conservative people said 2020, and we're here, and all we have is endless video conferencing. So what happened? Well, really, these demos are never robust once you take them out of the recording studio. In fact, the honest people will record lots of outtakes, and it's not yet clear if the ratio of success to failure is even close to 50%. Everything remains really hard. And of course, some people were a little bit too ambitious and actually started to deploy these techniques and tools out in hardware with real people. And this has resulted in numerous fatalities already. Incredibly unsafe behavior by industrial companies looking to get a jump on the space of self-driving have led to a lot of catastrophes already. So the real question is, how do we jump from some impressive demos into scalable autonomous driving, into well-automated supply chain and delivery services, into maybe even perhaps well-regulated, completely automated smart grids using a variety of renewable energy? This is going to require a bunch of new techniques from the machine learning community, the control theory community, and many others in order to get us to the stage of trustable, scalable, predictable, and reliable autonomy. Fortunately, we've seen interest not just from industry and government, but also academia in actually trying to pursue these goals in some kind of sensible form. I am probably best considered a theorist, and the theory community has really been coalescing around a bunch of interesting topics, trying to merge the fields of learning and control. I've been to many meetings just even in the past year. Really amazing workshop at the University of Washington that was sponsored by the NSF. The Information Theory and Applications had a whole, which is a long-running conference in San Diego, had a whole plenary session on control theory through a learning theory lens. And recently, in February, the Institute for Pure and Applied Math at UCLA hosted a week-long workshop on intersections between control learning and optimization. And this was sadly the last in-person meeting I attended before the coronavirus pandemic ended meetings for the foreseeable future in person. I was also an organizer of the Learning for Dynamics and Control conference, which we ended up having to be virtual in just a couple weeks ago at UC Berkeley. The first one of these meetings was held at MIT. With about 3 months of notice, the organizers put together a pretty impressive meeting with 400 participants and 20 speakers. And really the enthusiasm was just kind of, was palpable. So for the second edition, we decided to have contributions. We had 135 submissions, 99 accepted papers, and 14 contributed oral talks in addition to our keynote speakers. Now, we had hoped to host this in Berkeley. Unfortunately, it wasn't to be, but I hosted the AV from Berkeley in my garage. And it is kind of amazing how much you can do with a command center like this, 3 laptops, hooked together on the internet, but everything ran surprisingly smoothly. There was a lot of engagement in a live chat, and I think it was, given all of our circumstances, really quite an impressive and interesting and enthralling meeting. Now, what I want to describe today is my perspective of where the field is now. This will, of course, be very biased and based predominantly on research that has been done in my group. And what I'm hoping to really just kind of set up is a flavor for what are really some challenging problems that remain on the theoretical side of things that might actually allow us to take a baby step towards improvements in this intersection of dynamics, learning, and control. Now, I think one of the most important things that has happened over the past 2 years has been this community building. And indeed, I think that if we have to think a little bit about what are these communities bringing to the table, what exactly is machine learning? At the really broad and ambitious scale, machine learning is the field that uses past data to learn about or act upon the world. Data can be useful when your environments are too complex, or your sensing is too complex, or your models are too complex. And the hope is that collecting data from these systems and using that as a proxy for these more complicated descriptions can actually allow you to push far beyond your capabilities had you actually had to specify all of these complex modalities. Control is the study of using feedback to mitigate the effects of uncertainty. So we know that in this case, environments are uncertain, sensors are uncertain, and models are uncertain. And in some sense, these two fields, though they actually were started by the same people, seem to be taking two very different takes on the world. One very focused on feedback, one very focused on data. So again, control, the idea of using feedback to mitigate the effects of dynamic uncertainty, and machine learning, using past data to act upon the world. What we're hoping is that now that we have massive computers that we could put on board our autonomous system, that we can actually combine these two to get kind of the best of both worlds, being able to use feedback and data in tandem in a way to achieve systems that we were not able to build before. But of course, if we were a bit more humble, we would actually accept that these are just the aspirations of control and machine learning and not what they end up being in practice. In fact, the majority of control, some might even argue more than 95% of control, are simple PID controllers that are badly tuned in a variety of industrial settings. And if we're honest, most of ML is just non-parametric supervised prediction thrown out kind of haphazardly in a variety of industrial settings with not many guarantees. These are actually quite humble tools, and we are trying to achieve some ambitious goals. And I think it's important to keep in context that the problems we're hoping to solve are very hard, and our tools may be somewhat limited. So I'm not going to attempt to describe today some framework to solve all of our outstanding challenges in autonomy. Instead, what I'm hoping to describe is how to use a common language of optimization to perhaps take the best from dynamics and from machine learning, put these together, and solve some problems that we didn't know how to solve before. I'll then move at the end to describe some problems that I feel are immediately accessible, but yet still very challenging, that might take us again along that step towards solving some of these challenges in autonomous systems. So let's dive in to a common ground framework of optimal control. In optimal control, we seek to minimize some cost function subject to the dynamics given to us by physics and the environment, and we seek to find a policy that will minimize this cost. So the CT here indexes our cost function. If you maximize instead of minimize, you call this a reward. And perhaps the biggest difference between machine learning and control is that control theorists love to minimize and machine learning folks love to maximize. In this notation, xt is the state, ut is the input, and et is some noise process. Ft is the state transition function that governs our dynamics. And that we could have perhaps constraint sets, x and u. And tau is an observed trajectory. Now this again is our data, and what makes this a machine learning problem is how do we take that past data and turn it into these actions through a policy, pi. Pi is our optimization decision variable. We're trying to build systems that take this data and predict actions in order to minimize this cost. Now, if everything was fully specified, the problem of optimal control is simply an optimization problem. This can be solved by a variety of different tools, whether they be batch solvers or dynamic programming. The problem becomes more about learning when parts of the system are unknown, and we have to actually learn what exactly is happening in different regions of the space based on some kind of exploration. So for simplicity, we'll just take the case that the dynamics are unknown. And I feel like this is an illustrative example that allows us to kind of highlight a variety of different techniques that have been explored at this intersection of learning and control. And it is a perennial challenge to understand how to perform optimal control when the system is unknown. In other words, how well must we understand a system in order to control it? Now, there's a large variety of methods that have been proposed to solve this system when the dynamics are unknown. The simplest, and we'll spend a lot of time on these methods today, are called model-based methods, which try to actually fit a dynamical model to the data and then use this dynamical model in an optimal control context. Other methods are so-called model-free. Now, model-free is not a particularly well-defined term, but I'm just going to use that today to describe two different approaches to this problem. The first approach is called direct policy search. Direct policy search only uses trajectory data to map into actions. The whole goal is to find the policy, obviating the need to ever understand the dynamics of the system. And then there is approximate dynamic programming. In approximate dynamic programming, the idea is to estimate the cost function, often called the value function, as if we know the value function, then dynamic programming gives us a procedure to actually extract optimal policies. These two methods that are model-free essentially are ways around estimating dynamics models. The proponents of these methods argue that sometimes learning the dynamics is costly and overly so, because for particular tasks, you may only need a smaller amount of information. The model-based methods, on the other hand, really use dynamics and keep them as a central part of the program from beginning to end. Model-based RL is different than policy search methods and dynamic programming methods insofar as I could describe them on a single slide. In model-based reinforcement learning, all we would do was collect some data, and we know that the data should obey some kind of recurrence like this. the state at time t+1 should be some function of the current state, the control input, and some noise. We then could fit our dynamics using supervised learning. And this would just be least squares fit to the proposed model. Then we can solve some optimal control problem that approximates the original optimal control problem. Perhaps we would model a different part of the noise process, or we would take into account some kind of knowledge about what uncertainty we've introduced with our approximation from data. Now, model-based RL is really simple. And models enable a variety of things, as control theorists well know. Modularity, safety, robustness, and invalidation as some examples. So if we're going to throw out models for these other methods, we really need a good reason. Now, studying this problem in general is quite challenging, and I think part of why there's so much confusion in this space is because it's been hard to kind of nail down what exactly approximate dynamic programming and direct policy search can buy you over traditional models in control. And while people may assert that on certain demos, one of these three works better, I think it's important to kind of settle on simple baseline problems that allow us to really crisply theoretically distinguish between what the pros and cons are of these varied approaches. So what my group spent quite some time doing is studying the example of the linear quadratic regulator. LQR is a very, very simple example. It's the most classic optimization optimal control problem out there. There are a variety of reasons why it's important. It has an elegant dynamic programming solution. It has a closed form solution on the infinite time horizon. Even on that infinite time horizon, the solution, the optimal policy is just to take your state and multiply it by a matrix, and that gives you the optimal control action. We know that this actually has natural robustness insofar as it's very robust to misspecification in either the objective or the dynamics itself. LQR is also broadly applicable as is, and it is used in a variety of different contexts in model predictive control and other automatic control applications. And for us today, linear dynamics will be essential. That's been so far one of the few things we can analyze well. But the quadratic cost is not. The quadratic cost we keep around just because it allows us to have a baseline to which we can compare our other methods. So let's discuss how we might study the complexity of a particular algorithm for solving the linear quadratic regulator. Now again, we're going to assume that we don't know the matrices A and B in this expression. But we're going to assume that we can actually generate trajectories of length t with arbitrary input sequences u. And the challenge is, if you could pick the u however you want, to build a controller with the smallest error and a fixed sampling budget, which we could say is just n times t. And the question is, what's the optimal thing to do? And how many samples would you need to actually get near optimal control? Those are the two questions we really like to get to the bottom of. Now, the naive idea here is that we know that when A and B are known, the optimal thing to do would be to build a control of the form u equals k times x. And k can be solved by solving a Riccati equation. So an obvious strategy, which is usually called certainty equivalent control, is to estimate AB from data and then treat that AB as if it were true and build a control u equals k xt. That really should be our universal baseline. It's the obvious thing. It's something people have been doing probably since the 60s. And any other algorithm should be compared to that baseline. So my group actually spent some time trying to analyze some of these model-free methods and how they compare to this certainty equivalent baseline. So the first comparison was comparing to approximate dynamic programming. In this case, the simplest thing you could do is fix some controller and then figure out how many samples are required to estimate the value function. The value function is simply the cost associated with any initial condition x once you have committed to a control policy K. And the theorem proven by Stephen 2 is that there exists a family of LQR systems for which a model-free method, in this case the least squares temporal differencing method, requires a factor of d more data than the model-based method to achieve the same estimation performance, meaning that the number of samples required is a factor of the state dimension larger than what is required by this simple model-based baseline. Stephen also showed that you can't actually do better than the model-based method on this same family of LQR systems. Now, what about policy search methods? For policy search methods, in this case, we directly try to find the controller from interacting with the system, never trying to fit a dynamical model. In this case, there exists a family of LQR systems for which the model-free method, in this case, what is called policy gradient, requires a factor of d times t more data than the model-based method to achieve the same performance. That means that the longer the time horizon, the more data direct policy search needs to actually achieve the same performance of just fitting a model to the data and then exploiting that in an optimal control context. And again, for this same family, the best you can do is to use this model-based method. Now, these are both theoretical results. And the question is always, does this actually happen in practice? What we found is that even for very, very simple examples, you can actually see this trade-off quite clearly. So perhaps one of the simplest LQR examples would be a double integrator, where we just would like to minimize the value of the state and then have some quadratic penalty on the control cost as well. We ran policy gradient on this model, and we plot it here in blue. So here the error bars are showing that there's this blue shaded region, showing that the performance of policy gradient is highly variable. And moreover, it doesn't really get down to the optimal cost, which is shown in the dotted line here, until after about 30,000 samples from this very simple two-dimensional system. Now, the model-based method actually only requires 10 samples and then is indistinguishable, at least on this plot, from the true optimal value. So really, policy gradient requires a ton of data just to get even remotely close to a decent solution, whereas the simple baseline that most people use, system identification, followed by simple exploitation, already works after 10 samples on this simple problem. Now, given all the hype out there about the power of reinforcement learning and policy methods, I mean, it's been claimed that you could solve all sorts of amazing video games using this approach. It does seem like this is quite the extraordinary claim, that on this simple problem, it fares so poorly as compared to a very, very simple and obvious baseline. But of course, extraordinary claims require extraordinary evidence only when your prior is correct. Now, I was asked when I gave an earlier version of my talk, how can you could dismiss this field that has all this success? But if you actually look at what people say from the field, you dig in a little bit, you'll see that that success isn't quite so obvious. Indeed, if you just go and take the word of the OpenAI folks themselves, they'll say that reinforcement learning results are tricky to reproduce, performance is very noisy, algorithms have many moving parts, which allow for subtle bugs, and many papers don't report all the required tricks. RL algorithms are challenging to implement correctly. Good results typically only come after fixing many seemingly trivial bugs. These are both quotes from the OpenAI blog itself, and honestly, this is probably fine if you want to build cool demos to play 5x5 video games. It is not okay if you want to build technology for cars. And there have been a bunch of results over the past several years. I'm highlighting the first one, which was a really nice paper by Joëlle Pineau and her collaborators, which showed that actually that these reinforcement learning algorithms are not just data hungry, but they're incredibly fragile to initial conditions. And that by simply changing the random seed, you could take the same algorithm and see dramatically different performance curves in terms of how well the algorithms were performing with respect to time. What this means is that if you refactor your code, you will actually get different performance because you're going to be accessing the randomness in a different order. And the bottom plot here actually shows 3 different implementations of the same algorithm by the same author. And all that has happened is the GitHub version had changed. Clearly, this behavior is not the behavior we'd want in algorithms that are embedded in autonomy that we need to rely on. And there really has to be a better way. So let's come back to our optimal control problem and think about what exactly we have to take in mind in order to get really reliable autonomous systems. We know that our dynamics might be uncertain. Our costs might change over time, and we might have to impose safety constraints. And so one way forward, and something we've definitely been thinking about a lot in my research group, and I know there are lots of people out there who've been thinking about different ways to incorporate ideas from robust control as a way to mitigate the effects of quantified statistical uncertainties. And I think what makes this time very interesting is that high-dimensional statistics, aided by all of the excitement of machine learning, has come a long way in the past 20 years. And robust control itself can now meet this new statistical quantification in a new way. And we can get a lot of new interesting results out of this. So let me walk you through one. Again, now just going back to model-based methods and focusing on LQR to see what we can learn. So we'll just, again, consider this case when we have uncertain dynamics and use robust control as a way to mitigate the uncertainty in those dynamics. So let's say we've estimated an A hat, B hat, that is a surrogate model estimate from some data. Let's say we've also quantified uncertainty using techniques from statistical learning theory to really understand how close A hat is to the true A. So epsilon A here is likely measuring error in some metric with respect to how close we are to the true A. So let's look at 2 different approaches that are optimal control based to solving the control problem given this data. We can either ignore the estimation errors and run what's called certainty equivalent control. Again, just treating the A and B as A hat and B hat as if they were true, plugging them in and solving the optimal control problem. Or we could solve robust LQR. In robust LQR, what we'll do is solve almost the same problem, except we'll add these delta uncertainties. The deltas here are representing our errors in the matrices A hat and B hat. And we know that they're bounded by our uncertainty quantification. So what we'll do is minimize the cost subject to the worst case realization of delta A and delta B. Now we can merge techniques from high-dimensional statistics and robust control to actually get insights about how much data is required to achieve reasonable cost on the original LQR problem, even though we don't know the true A and true B for this problem. So we have 2 theorems that we were able to prove. The first is about the robust LQR. And I find it interesting that we actually proved the robust theorem 2 years before we proved the not robust theorem. And there are a variety of reasons for this. And I find it actually quite interesting that at the end of the day, we came back to showing that certainty equivalence, at least when there's enough data, is better than robust control. And I'll discuss this again in a moment. But let's just unpack these bounds. So what we're comparing here is the cost of my controller that was synthesized with either robust control or with certainty equivalence. And J star is the best you could do if you actually knew the true A and B. And we show that the robust method scales as the square root of the number of parameters divided by the number of samples. On the other hand, the error uncertainty equivalence scales as the number of parameters divided by the number of samples with no square root. So this classic algorithm that we have been using in controls for over 50 years turns out to actually be a particularly efficient method. It uses asymptotically, it uses less data than the robust method. Now, this is just comparing upper bounds, so we actually have to look at what happens in practice. And what happens in practice is quite informative, because what we saw in certainty equivalence when we were trying to analyze this was that it required a lot of clever thinking about how to put these pieces together to really guarantee the stability. And it doesn't always work. And let's actually show that these upper bounds are not all of the story. So here in blue, we plot the performance of robust LQR on a toy example that we created. This was a 3x3 example. The details don't particularly matter. We could construct a variety of other scenarios. But at least the plot here does seem to capture what we see in a variety of different settings. The x-axis here is the number of samples. The y-axis is the relative cost. And the orange plot is what we get for certainty equivalence. So what we see is that certainty equivalence has very large error bars, up to about 400 samples. At that point, the error bars get significantly smaller, and even after 300 samples, the median performance is better than the robust method. Now, the error bars for the small number of samples are quite large for certainty equivalence, whereas for robust LQR, the error bars remain quite low. If we look at this a bit differently, we actually see why the robustness can be useful. We ran multiple simulations here trying to plot kind of the average case behavior. And what we found is that in this particular model, the certainty equivalent method was actually returning unstable systems a large proportion of the time. Even at this point of 600 samples, about 10% of the time it would return an unstable closed-loop solution. On the other hand, robust LQR has this nice property that if it returns a solution at all, it returns a stable solution. And so we see quite quickly that we get a stable, though not particularly highly performing, solution to the problem. So there's this nice balance, which we've known for quite some time, between robustness and performance. And the trying to figure out where you are is really just a matter of understanding how much data you have acquired and understanding how well you can quantify the uncertainty in your estimates when you're building these control systems. So the takeaway from our work in LQR is that we really quantified how much data you need to achieve near optimal performance. We found that model-based methods across the board were more data efficient and more robust than model-free ones. And this was both in theory and in practice. And explicitly accounting for uncertainty can give really good guarantees on closed-loop performance. We found that you really need robustness when your estimation errors are large. And there are pretty clean and nice algorithmic ways to add that robustness to these optimal control problems. And when the estimation errors are small, meaning that you're willing to spend time in the laboratory really nailing down the model, you don't actually have to consider robustness to get good performance with reasonable safety. In some sense, this result's a little disappointing because we spent all of this time studying all these cool tools in high dimensional statistics and in robust control and just came back to the conclusion that what we've been doing since the 50s was probably good enough. It didn't really give us a new algorithm that was going to be profoundly better than what we'd already been doing. But on the other hand, as I've been mentioning, I think the important thing here was establishing bridges between machine learning and control, putting these two fields kind of on the same footing and seeing what they could teach each other. And also what has been useful is that we were actually able to get insights into some of the more complicated nonlinear models that people are currently studying. Indeed, a principle that has guided my research in machine learning for quite some time is that if you have an algorithm that does crazy things when you restrict it to linear models, it's probably doing crazy things on those complex nonlinear models too. And so when my group returned and tried to study nonlinear models using what we learned from LQR, we found that very simple static linear policies were actually outperforming deep reinforcement learning on all of the benchmarks that deep reinforcement learning people had been working on. And these policies can be found with really dumb and simple algorithms. And what we found beyond that was that these simple little linear policies that were put into a model-free environment were still far outperformed by model predictive control. And indeed, not just any model predictive control, but model predictive control from 8 years ago was far better performing than these fancy reinforcement learning methods or our linear methods that were actually better than these deep reinforcement learning methods. Model-based methods seem to perform better than model-free ones in theory and practice in every example we've been able to look at. Data alone is not going to buy us a ticket to safe autonomous systems. Models enable so many powerful tools for modularity, safety, robustness, that if we're going to throw them out, we really need a good reason to. And I would argue that we have not seen any evidence so far that that should be the case. And the other really important lesson is that sometimes simple algorithms are the best you can do, but proving that it's the best you can do can be really, really hard. It's very interesting how sometimes the provable method is often less well-performing than some other method that's much simpler. We saw this with certainty equivalence in the case of LQR. We see this in a variety of other contexts. And I'm going to touch on this a little bit more later because I still think it's a very valuable exercise to go in and try to understand why simple things work so well when they do. So at this point, I'd like to turn and look at some of the possible way forward. I'd like to think a little bit about what theory-minded folks might work on in the short term, the very near future, that might help us push paths towards improving learning systems and very complex feedback loops. And I'm going to focus on a few challenges that I think might help us make some real important and impactful near-term progress. So I think the first thing to emphasize is that machine learning itself is not what we would consider a robust technology. We've been using benchmarks and seeing really amazing performance in machine learning, but the kinds of success rates that we're achieving are in the range of, let's say, 90% accuracy on this amazing ImageNet benchmark. The challenge, of course, is how do you go from methods that fail once out of every 10 times to methods that fail once every billion times? And that is a supreme challenge. In machine learning, we're currently seeing significant diminishing returns, where to eke out little bitty performances on our top benchmarks are requiring more and more computation, to the point now where this is only accessible to some of the richest companies in the world. We've also seen that they have significant fragility when the data changes. And when the data changes to be stuff that you haven't seen in the laboratory, large failures occur. So how can we make machine learning more robust? And how can we approach the failure rates that are needed for safe and reliable autonomy? How can we establish testing protocols that assure that we actually have those low failure rates? These are some questions that I think would be really important to ask moving forward. So another challenge I think is important, as I mentioned at the beginning, to recognize that machine learning successes are almost all in non-parametric prediction. Machine learning is mostly used for taking images and then labeling words on top of them. And you do this by having large catalogs of data. And this enables really powerful tools like translation and translation from images. And it also kind of enables the whole backbone of recommendation on the internet. So the question is, how do we actually take what machine learning is really good at? Machine learning is not very good, as we've seen, at mapping data into control policies, but is really good at mapping images into really concise descriptions that we didn't actually think were possible up until a few years ago. So the question is, when we start to put these into control loops, how can we think of machine learning systems almost as virtual sensors? How can we incorporate this kind of uncertain predictive perception in trustable and scalable autonomy? So I still remain baffled by how model predictive control is consistently underappreciated. We'll commonly see the same task in the same meeting, one task done on a robot using some sort of deep reinforcement learning, and the other done using model predictive control. And the disparity in their performances are just stark. So here's an example of some work done at DeepMind and some work done at Berkeley. On the left, we're going to have a video of a robot trying to catch a ball in a cup. You'll see that the cup is quite large. It's like a waste paper basket, and the ball is a tennis ball. This system uses two very expensive cameras that you could actually see in the background there, and an elaborate robotic arm system. On the right, we're going to see the same experiment, except with your standard ball in the cup toy that you might buy for your 7-year-old to keep him busy during quarantine. This is controlled by a robotic arm, and it uses only a single camera. So let's first watch the performance of the DeepMind system. Now that's after 4,000 episodes of training, it can actually start to catch the ball in the waste paper basket. Whereas the Borelli lab is really only trying to do learning because of the vision sensor and just uses some very simple Newtonian physics and MPC with a learning component attached on the end. And this is what their performance is. If you only saw these two videos, I can't fathom why you invest all of your assets into deep reinforcement learning. I understand that there are still a lot of diehards out there, whether they be at DeepMind or OpenAI or at other places. But I want to make a real constructive point that so many in the control community and the machine learning community are spending time studying RL algorithms. But there are really very few people, especially in the machine learning community, who are trying to analyze why MPC is so successful, especially when it's coupled with machine learning. I'm not arguing that we should just give up on reinforcement learning necessarily, but I would like us to rebalance our mental resources to at least spend some more time understanding the power and limits of learning augmented model predictive control. So one of the grand goals in reinforcement learning is to use function approximation algorithms to estimate value functions. The conventional wisdom in RL asserts that the world is just some giant Markov decision process, and once you've computed the value function, you can just greedily maximize it, and you'll just win at every objective that you care to win at. Now, we know that this approach doesn't really work for robots. People have been trying to build reinforcement learning-based robots for quite some time, and as we just saw in the previous slide, they're nowhere near close to the performance that you can get out of standard control theoretic approaches. Now, part of the reason why people are so excited, however, was because of the success of AlphaGo. AlphaGo worked really well, beyond our wildest dreams, and really just conquered that game on a time scale that I think none of us really expected. But at some point, I think we all have to come to terms with the fact that games are just not the real world. I'd argue that reinforcement learning does work really well in the real world. It doesn't. Greedy value function exploitation works well for games. It's very limited for control, but it works really well in internet systems that make recommendations based on your past behavior and forward you content on a variety of different platforms. The standard algorithm for ranking, for advertising, for recommendation is based on something called contextual bandits. Systems simply use past data to estimate value functions, and then they choose the item to show you that maximizes their predicted value at the next step. We don't typically describe these as reinforcement learning, but this is really what they are. They are instances of what's called the greedy contextual bandit, and this algorithm makes tech companies unbounded amounts of money. But many people have also pointed out that this algorithm leads to misinformation, polarization, and radicalization. So while I think we've spent a lot of time motivating reinforcement learning by the success of AlphaGo, I think if we had turned around and tried to motivate our dive into reinforcement learning based on Facebook, we'd probably be taking a very different approach. It would be a lot more clear why reinforcement learning is actually quite terrifying and dangerous, and it's one whose limitations we really need to understand so we can build safer tools. So along the lines of safety, let me just close with one last example. And that is taking some of the lessons that we learned about optimal control in the 70s and trying to recontextualize them in our 2020 time. As an example, we learned in the 70s that optimization without understanding fundamental limits is inherently dangerous. And probably the best example, the most concise example, is a paper by John Doyle, which showed that there are no guaranteed margins for LQG regulators. Still has the best abstract out of any paper I've ever read. In the machine learning context, we could actually think about what's happening here as follows. Let's consider this LQG problem, where instead of having observing state, we observe just one component of the state. And we're still solving a linear quadratic problem, but now we actually have to filter to do a state estimate. What's fascinating, and this is really just a generalization of Doyle's example, is that if you improve your sensor so that the ET signal is effectively going to zero, and you optimize, then this system becomes arbitrarily fragile if you take out the solution that comes from the LQG solution. This, if you told this to a machine learning researcher, would be perplexing. You're telling them that you're improving their prediction system to the point where the predictor works exceptionally well and there's just no noise in their sensor. And that actually makes the system more fragile to misspecification. These kinds of lessons are ones that I think we really do need to modernize and to figure out exactly how can machine learning be put into these feedback loops in a way that takes the best of the data and doesn't open us up to unforeseen catastrophes. So I'd like to thank all of you for listening. I think we've really made some pretty amazing progress over the past half decade, understanding what we can and cannot do at the intersection of learning and control. Bringing these two fields together has required a lot of community building, a lot of bridge building. We've established new conferences. We've had a bunch of great workshops, and we're really starting to get a feel for what we're capable of. And we haven't really made this big leap into actually really pushing what we know into this kind of next frontier of autonomy. But I'm excited to take those next steps, and I can only imagine what the next 5 years will bring. Thanks again for listening. This has been an interesting experience, recording a video in my garage and not getting your reaction, but I hope that you enjoyed it, and I hope that you enjoy the rest of the Congress.